All right. Hello, everybody. We're going to talk about electrical safety here. Now, this presentation is quite long and involved, and it's pretty general about electrical safety. So there's a lot of good stuff in it, but and then we're going to talk about the set parts of OSHA that have that address electrical safety, particularly in separate videos. But this one's a real general video about electricity, and let's get started. We're going to cover the basics of electricity, how to protect against electrical hazards. And most of it's from an OSHA publication, so I didn't make this stuff up. Some statistics, number of fatal electrical accidents by event code. Now, as you can see, this goes back to 92 to 2015. And in it, around 92, there was about 350 around their deaths per year. It's a lot of people dying. Somebody every day. And then but got down to about 150, 130 something in 2015. That's pretty good. Knocked it over less than half. Still too many. But and also you probably have to remember, probably in that time, more people were around too. So it's coming down. And this is by age group. You can see 18 to 19, 20 to 24, 25 to 34. And as people get older, maybe they do get a little bit wiser when it comes to electricity. I don't know. Here, 25 to 34 kind of peaked here. And as people get older, that goes down quite a bit. So maybe there is some truth to that. All right. What is electricity? Well, it consists of three things, basically: voltage, which is measured in volts; current, measured in amperes, which are amps; and resistance, which is measured in ohms. The primary factor for injury from an electrical source is amps. The average individual cannot release his or her grip on a handheld current source above 12 milliamps. That's 12,000, 1,000th of an amp. That's not a lot. High voltage energy sources found in industrial settings are extremely hazardous. Most household electricity is 120, 240 volts and 15 to 20 amps. Usually it's 110. We usually call it 110 to 120, same thing. Industrial settings have regular 120 and 240 volt, as well as high voltage equipment. It can go up extremely high. It varies, but it's not unusual to have 440 or N up. NEC, National Electrical Code, defines high voltage as above 600 volts. Now, most people would think high voltage is anything above 110 or 120, right? But nope, NEC defines high voltage as above 600 volts. Tasers use 20,000 to 150,000, but only 2 volts, but only 2 to 3 milliamps. A lot of voltage, but only very few milliamps. So the amps would get you, although the voltage there in a taser is gonna mess with you, though. Electrical hazards are best dealt with through design. And as we know, in safety, pretty much a lot of things can be dealt with in design. This includes safe installation in accordance with NFPA 70E, Standard for Electrical Safety in the Workplace, the National Electrical Code, NEC, and local electrical code. The NEC is the minimum standard, but provides the most comprehensive document dealing with the installation and use of electric equipment. So if you're going to put it in, you want to have the NEC. Now, again, I'm not expecting anybody to be electricians, but so what affects the flow of electricity? Well, it flows more easily through some materials than others. Some substances, such as metals, generally offer very little resistance to the flow of electric current and are called conductors. A common but perhaps overlooked conductor is the surface or subsurface of the earth. Glass, plastic, porcelain, clay, pottery, dry wood, and similar substances generally slow or stop the flow of electricity. They're called insulators. Even air, normally an insulator, can become a conductor, as occurs during an arc or lightning stroke. How does water affect the flow of electricity? Well, pure water, is a poor conductor. I didn't realize that either before I saw this. But small amounts of impurities in water, like salt, acids, solvents, and other materials, can turn water itself and substances that generally act as insulators into conductors or better conductors. Dry wood, for example, generally slows or stops the flow of electricity. But when saturated with water, wood turns into a conductor. The same is true of human skin. Dry skin has a fairly high resistance to electric current, but when skin is moist or wet, it acts as a conductor. This means that anyone working with electricity in a damp or wet environment needs to exercise extra caution to prevent electrical hazards. What causes shocks? Electricity travels in closed circuits, normally through a conductor. But sometimes a person's body, an efficient conductor of electricity, mistakenly becomes part of the electric circuit. This can cause an electrical shock. Shocks occur when a person's body completes the current path with either both wires of an electric circuit, one wire of an energized circuit, and the ground, a metal part that accidentally becomes energized due, for example, to a break in its insulation, or another conductor that is carrying a current. When a person receives a shock, electricity flows between parts of the body or through the body to a ground or to earth. What effect do shocks have on the body? An electric shock can result in anything from a slight tingling sensation to immediate cardiac arrest. The severity depends on the following: the amount of current flowing through the body, the current's path through the body, the length of time the body remains in the circuit, and the current's frequency. As little as 100 milliamps at 60 hertz can be fatal. The next table on the next slide shows the general relationship between the amount of current received and the reaction when current flows from the hand to the foot for just 1 second. So from the hand to the foot, it's going through your body for just 1 second. Below 1 milliamp, generally not even perceptible. 5 milliamperes, a faint tingle. 60 to 30 milliamps, painful shock, loss of muscular control. Individual cannot let go, but can be thrown away from the circuit if extensor muscles are stimulated. So you have flexor muscles and extensor muscles. 50 to 150 milliamps, extreme pain, respiratory arrest, severe muscular contractions, death is possible. Now we're talking milliamps here, thousands of an amp, not even an amp yet. 1,000 to 4,300 milliamps, which would be 1 to 4.3 amps, rhythmic pumping action of the heart ceases. You don't want that to happen, believe me. Muscular contraction and nerve damage occurs, death likely. 10,000 milliamps, cardiac arrest, severe burns, death probable. So what kind of burns can a shock cause? Burns are the most common shock-related injury. An electrical accident can result in electrical burn, arc burn, thermal contact burn, or a combination of burns. Electrical burns are among the most serious burns and require immediate medical attention. They occur when electric current flows through tissues or bone, generating heat that causes damage to the tissue. Arc or flash burns results from a high temperatures caused by an electric arc or explosion near the body. These burns should be treated promptly. Thermal contact burns are caused when the skin touches hot surfaces or overheated electrical conductors, conduits, or other energized equipment. Thermal burns can also be caused when clothing catches on fire, as may occur when electric arc is produced. Why do people sometimes freeze when they're shocked? When a person receives an electrical shock, sometimes the electrical stimulation causes the muscles to contract, like this. This freezing effect makes the person unable to pull free of the circuit. It is extremely dangerous because it increases the length of exposure to electricity and because the current causes blisters, which reduce the body's resistance and increases the current. The longer the exposure, the greater risk of serious injury. Longer exposures at even relatively low voltages can be just as dangerous as short exposures at higher voltages. Low voltage does not imply low hazard. What should you do if someone freezes to a live electrical contact? This is good to know. If a person is frozen to a live electrical contact, shut off the current immediately. That is number one. If you shut it off as soon as you can. If this is not possible, use boards, poles, or sticks made of wood or any other non-conducting materials and safely push or pull the person away from the contact. It's important to act quickly, but remember to protect yourself as well from electrical shock. How can you tell if a shock is serious? A severe shock can cause considerably more damage than meets the eye. The victim may suffer internal hemorrhages and destruction of tissues, nerves, and muscles that aren't really visible. Renal damage can also occur. If you or a coworker receives a shock, seek emergency medical help immediately. In other words, err on the side of caution. Get medical help when there's a shock. What's the best way to protect yourself against electrical hazards? Most electrical accidents result from one of the following three things, or three factors: unsafe equipment or installation, unsafe environment, or unsafe work practices. Well, consider for a lot of accidents. Some ways to prevent these accidents are through the use of insulation, guarding, grounding, electrical protective devices, and safe work practices. Insulators, what protection does insulation provide? Insulators such as glass, mica, rubber, or plastic used to coat metals and other conductors help stop or reduce the flow of electrical current. This helps prevent shock, fires, and short circuits. To be effective, the insulation must be suitable for the voltage used and conditions such as temperature and other environmental factors like moisture, oil, gasoline, corrosive fumes, or other substances that could cause the insulator to fail. What is guarding and what protection does it offer? Guarding involves locating or enclosing electrical equipment to make sure people don't actually come into contact with its live parts. Effective guarding requires equipment with exposed parts operating at 50 volts or more to be placed where it is accessible only to authorized people qualified to work with it. Recommended locations are a room, vault, or similar enclosure, a balcony, gallery, or elevated platform, or a site elevated 8 feet or more above the floor. Sturdy permanent screens can also serve as effective guards. Yeah, I've had sturdy permanent screens. I have never seen a sturdy permanent screen, but I guess you could have one. And the elevated stuff, not a bad idea. If you elevate something 8 feet. What signage is needed? Conspicuous signs must be posted at the entrances to electrical rooms and similarly guarded locations to alert people to the electrical hazard and to forbid entry to unauthorized people. Signs may contain the word danger, warning, or caution, and beneath that, appropriate, concise wording that alerts people to keep the hazard or to people to the hazard, or gives an instruction such as danger, high voltage, keep out. I'm guessing if you have an electrical room, you want to see danger, high voltage, keep out, or authorized personnel only, something like that. What is grounding? What protection does it offer? Grounding is a tool or electrical system means intentionally creating a low grounding. A tool or electrical system means intentionally creating a low resistance path that connects to the earth. This prevents the buildup of voltages that could cause an electrical accident. In other words, when that voltage gets away from something where it should be, it's going to go to ground. Grounding is normally a secondary protective measure to protect against electric shock. It does not guarantee that you won't get a shock or be injured or killed by an electrical current. It will, however, substantially reduce the risk, especially when used in combination with other safety measures discussed in this booklet. An equipment ground helps protect the equipment operator. It furnishes a second path for the current to pass through from the tool or machine to the ground. This additional ground safeguards the operator if a malfunction causes the tool's metal frame to become energized. The resulting flow of current may activate the circuit protection devices. What are circuit protection devices and how do they work? Circuit protection devices limit or stop the flow of current automatically in the event of a ground fault overload, or short circuit in the wiring system. Well-known examples of these devices are fuses, circuit breakers, ground fault circuit interrupters, and arc fault circuit interrupters. Us old people are familiar with fuses, but fuses are still around. Circuit breakers are way more common. Ground fault circuit interrupters become very common, which is good, and arc fault circuit interrupters. Fuses and circuit breakers open or break the circuit automatically when too much current flows through them. When that happens, fuses melt and circuit breakers trip the circuit open. Fuses and circuit breakers are designed to protect conductors and equipment. They prevent wires and other components from overheating and open the circuit when there is a risk of a ground fault. Ground fault circuit interrupters, or GFCIs, are used in wet locations, construction sites, and other high-risk areas. These devices interrupt the flow of electricity within as little as 1/40th of a second to prevent electrocution. GFCIs compare the amount of current going into electrical equipment with the amount of current returning from it along the circuit conductors. If the difference exceeds 5 milliamperes, the device automatically shuts off the electrical power. These things are great. Any houses that have been built in the last probably 30 years, because our house is a little over 30 years old now. We have GFCIs in the kitchen, by the kitchen sink, and in the bathroom too. And they're great. The guy that invented the GFCI, when he was going around selling it, he would put his daughter, an adult daughter, in a bikini in a bathtub and throw a radio in it and plug in a radio to show that it would shut the electricity off. Now that's confidence. Arc fault devices provide protection from the effects of arc faults by recognizing characteristics unique to arcing and by functioning to de-energize the circuit when an arc fault is detected. What work practices help protect you against electrical hazards? Electrical accidents are largely preventable through safe work practices. Example of these practices include the following: de-energizing electrical equipment before inspection or repair. That has to come with a big duh. Keeping electric tools properly maintained. Exercising caution when working near energized lines, and using appropriate protective equipment. How can you protect yourself against metal parts that become energized? A break in electric tools or machine's insulation can cause its metal parts to become hot or energized, meaning that they conduct electricity. Touching these energized parts can result in an electric shock, burn, or electrocution. The best way to protect yourself when using electrical tools or machines is to establish a low resistance path from the device's metallic case to the ground. You ground the case. This requires an equipment grounding conductor, a low resistance wire that directs unwanted current directly to the ground. A properly installed grounding conductor has a low resistance to ground and greatly reduces the amount of current that passes through your body. Cord and plug equipment with a 3-prong plug is a common example of equipment incorporating this ground conductor. So everybody knows what a 3-prong plug is, I hope. And if you have a 3-prong plug, you should have that third grounding one on there. Another form of protection is to use listed or labeled portable tools and appliances protected by an approved system of double insulation or its equivalent. Where such a system is employed, it must be marked distinctively to indicate that the tool or appliance uses an approved double insulation system. And how can you tell if a tool or something like that is double insulated? On its nameplate will have a square within a square, and that makes sense, and that's double insulated. If you go to Lowe's or any store like that, and you get down where they sell the saws and stuff like that, power tools, and you look at the name, then you'll see just a 2-prong plug in a lot of them. But if you look at the name, at the nameplate, or whatever you want to call it, on it, it'll have that square within a square, showing you that it's double insulated. How can you prevent an accidental or unexpected equipment startup? Proper lockout-tagout procedures protect you from the dangers of the accidental or unexpected startup of electrical equipment and are required for general industry by OSHA Standard 1910.333 and 1926.417. These procedures ensure that electrical equipment is de-energized before it is repaired or inspected and protects you against electrocution or shock. Now, the OSHA standard also references 1910.147, but there's also lockout procedures in 1910.333. Anything that starts 1910 with a 3 is electrical. The first step before beginning any inspection or repair job is to turn the current off at the switch box and padlock the switch in the off position. This applies even on so-called low-voltage circuits. Securely tagging the switch or controls of the machine or equipment being locked out of service clarifies to everyone in the area which equipment or circuits are being inspected or repaired. When they say tagging, it's not about tag out, it's being lockout. Oh, how can you prevent an accidental or unexpected equipment startup? Only qualified electricians who have been trained in safe lockout procedures should maintain electrical equipment. No 2 of the locks used should match, and each key should fit just 1 lock. In addition, one individual lock and key should be issued to each maintenance worker authorized to lock out and tag the equipment. All employees who repair a given piece of equipment should lock out its switch with an individual lock. Only authorized workers should be permitted to remove it. Okay, that's basically lockout 101. Employees unqualified to work with electricity, as well as mechanical equipment, should remain at least 10 feet away from overhead power lines. If the voltage is more than 50,000 volts, the clearance increases by 4 inches for each additional 10,000 volts. Overhead power lines, even staying away from. There was construction going on in California, in actually a freeway they were building, and there was 3 workers that were basically on break. It was lunchtime, so they were going to eat lunch. So there was a chain link fence there. So they were leaning up against this chain link fence, having lunch. When a little further away, a piece of equipment, I don't know what it was, some kind of crane or something, was in contact with this chain link fence, and also touched the overhead power lines and killed all 3 of them. They were just standing there eating their lunch. When mechanical equipment is operated near overhead lines, employees standing on the ground should avoid contact with the equipment unless it is located outside the danger zone. When factoring the safe standoff distance, be sure to consider the equipment's maximum reach. What protection does personal protective equipment offer? Employees who work directly with electricity should use the personal protective equipment required for the jobs they perform. This equipment may include rubber insulating gloves, hoods, sleeves, matting, blankets, line hose, and industrial protective helmets designed to reduce electrical shock hazard. What role do tools play? Appropriate and properly maintained tools help protect workers against electric hazards. It's important to maintain tools regularly because it prevents them from deteriorating and becoming dangerous. Check each tool before using it. If you find a defect, immediately remove it from service and tag it so no one will use it until it has been repaired or replaced. When using a tool to handle energized conductors, check to make sure it is designed and constructed to withstand the voltages and stresses to which it has been exposed or will be exposed. What protection does PPE offer? Employees who work directly with electricity should use the personal protective equipment required for the jobs they perform. Again, this equipment may include rubber insulating gloves, hood sleeves, matting, blankets, line. I think I just said that. All right. What special training do employees need? All employees should be trained to be thoroughly familiar with the safety procedures for their particular jobs. Moreover, good judgment and common sense are integral to preventing electrical accidents. I go out on a limb and say good judgment and common sense are integral to preventing almost all accidents. Good judgment and common sense. When working on electrical equipment, for example, some basic procedures to follow are to de-energize the equipment, use lockout and tag procedures to ensure that the equipment remains de-energized. And you notice here they're saying things a little differently. It's not lockout, tag out. Lockout and the tag. Put a tag on that so they know which equipment is locked out. Use insulating protective equipment and maintain a safe distance from energized parts. OSHA regulations for electricity in subpart S, all of these here. And then all the ones, we're going to just briefly touch on 301 through 308 because they get very detailed. And then we're going to touch on 331 to 335 separately because they get more involved in the safety part of it. So 301, just an introduction, basically tells you where stuff's at. 302 is electrical utilization systems. It's pretty technical, and I'm going to bring up one or two from each of these maybe that I thought interesting. This is 1910.302 of applicability of requirements for disconnecting means. The requirements in 1910.147 C2 III that energy isolating devices be capable of accepting a lockout device whenever a replacement or major repair, renovation, or modification of a machine or equipment is performed, and whenever new machines or equipment is installed. And here's a case where OSHA's electrical 302 is referencing 147 lockout, which is a great idea. And it states if any new modified equipment or new equipment, you have to make sure it can be locked out. And that's obviously a great idea. That's why the vast majority of all equipment out there today can be locked out. 303 is general. It gets lots of technical stuff, but the next two slides are of interest. In locations where electric equipment is likely to be exposed to physical damage, enclosures or guards shall be so arranged and of such strength as to prevent such damage. Entrances to rooms and other guarded locations containing exposed live parts should be marked with conspicuous warning signs forbidding unqualified persons to enter. Frequently in plants, there's electrical panels out in a plant. It happens a lot. And when most plants that I've ever been in put up bollards, which is a cement post in the ground. Maybe it's covered with some rubber, but it's going to prevent a forklift from even hitting it. So you don't want somebody with a deranged forklift hitting this electrical power, the electrical panels. That's for sure. And then entrances to rooms and other guarded locations have the warning signs, and probably should be locked too, but definitely have warning signs on them, as we discussed earlier. Workspace about equipment. Sufficient space shall be provided and maintained about electrical equipment to permit ready and safe operation and maintenance of such equipment. Where energized parts are exposed, the minimum clear workspace may not be less than 6.5 feet high, measured vertically from the floor platform, or less than 3 feet wide, measured parallel to the equipment. In all cases, the workspace shall be adequate to permit at least a 90-degree opening of doors or hinge panels. Systems over 600 volts nominal. This paragraph covers the general requirements for all circuits and equipment operated over 600 volts. That's 308A. Okay, regulations for electricity in subpart S, safety-related work practices are in section 331, and we're going to talk about them individually. Qualified persons, one who has received training in and has demonstrated skills and knowledge in the construction and operation of electric equipment and installations and the hazards involved. They have to be trained in it and have demonstrated skills and knowledge. Now, if you didn't document it, you didn't do it, right? So training has to be documented, and demonstrated skills and knowledge. Demonstration of that skill and knowledge should be documented too. Note 1 to the definition of a qualified person. Now, qualified person comes up a lot in OSHA. So here's now 1910.399, electrical definitions handles it. Whether an employee is considered to be a qualified person will depend upon various circumstances in the workplace. For example, it is possible and in fact likely for an individual to be considered qualified with regard to certain equipment in the workplace, but unqualified as to other equipment. See 1910.332b3 for training requirements that specifically apply to qualified persons. This makes a lot of sense. In a plant, you can have a lot of different electrical equipment, and you may be qualified to work on one type of equipment, but not on another. Very possible. So, and now they have note 2 to qualified person. An employee who is undergoing on-the-job training and who, in the course of such training, has demonstrated an ability to perform duties safely at his or her level of training, and who is under the direct supervision of a qualified person, is considered to be a qualified person for the performance of those duties. So they're allowing for a trainee who's on the job training and has demonstrated the ability to perform duties safely at that level of training and is under the direct supervision of a qualified person. Direct supervision. That doesn't mean the guy's on the other side of the plant. That means direct supervision. That person's got to be right there supervising the person directly. Okay, again, we're talking about these in separate videos. Okay, what's the value of a safety and health program in controlling electrical hazards? Everyone has the right to work in a safe environment. Safety and health add value to any business and workplace. Through cooperative efforts, employers and employees can learn to identify and eliminate or control electrical hazards. Every good safety and health program provides measures to control electrical hazards. The measures suggested herein should be helpful in establishing such a program. The responsibility for this program should be delegated to someone with a complete knowledge of electricity, electrical work practices, and the appropriate OSHA standards for installation and performance. That's it. So that's quite a bit there, but there's a lot to. Oops, that's good. Okay. There's a lot to the electrical standards that we're not covered in here because they're way too detailed and specific and way beyond the scope of this class. But you need to know a little bit about electricity, and you know that we're going to talk about more electrical safety in a further video. So stay safe.